Hello students, now let us start with the next lecture, that is about the average atomic mass. So we have been discussing about atomic mass in the earlier lecture. Now we'll talk about average atomic mass. Now you know that many naturally occurring elements, they exist as more than one isotope. So here you can see carbon, it exists in three different isotopes and their relative abundance is shown here. This carbon 12, the relative abundance is 98.892 with atomic mass 12, C13 with 1.108 and its atomic mass is found to be 13.00335, and C14, which is a quite in less amount, that is 2 into 10 raised to minus 10, and atomic mass was found to be 14.00317. Now when we are supposed to use carbon, atomic mass of carbon as an element, we have to take this the average of these atomic masses of all the three isotopes. So you can write this average atomic mass, that is average atomic mass of this carbon. You can calculate very easily. You just have to take the average of this. So this is the percentage abundance, 98.892. It has to be multiplied by 12, that is this atomic mass, plus 1.108 multiplied by 13.00335, that is the atomic mass of this C13, plus you add 2 into 10 raised to minus 10, that is the percent relative abundance of C14 isotope, into its atomic mass, which was found to be 14.00317. So you add up this and divide it by 100, that will give you, which will be equal to 12 point. If you solve this whole thing, this thing plus this one and this, so you'll get the answer 12.011 units. So this is nothing but the average atomic mass which we take generally while solving the problem based on the molecular mass or the atomic mass of the carbon atom. So this is about the average atomic mass, means we are just taking the average of the relative abundance of different isotopes multiplied by its atomic mass. You will get the average atomic mass of this particular element. We had taken the example of carbon atom here. Now next you can solve if the isotopes are given and their masses are given, how will you calculate the percentage abundance or the relative abundance of those. Now here is the example, that is chlorine has two stable isotopes, Cl35 and Cl37 with atomic masses. These are the atomic masses of this Cl35 and Cl37 respectively. And if the average atomic mass, this is also given, how will you calculate the percentage abundance of this? Means what is the percentage abundance of this elements? Here Cl35 and Cl37. Okay. So now you can solve this problem this way. Suppose the natural abundance of this Cl35, natural abundance of this Cl35, if you take it as x, because we are supposed to calculate this x percent, and that of Cl37 will be 100 minus x. Okay, so this is x and 100 minus x will be for this Cl37. 100 minus x percent. Now we are supposed to calculate the value for this x. This can be done because we are having this information with us, 34.968 and 36.956. So by using this information, you can be able to find out the average atomic mass first. So first calculate average atomic mass. I tried to fix this whole thing on this screen itself, on this slide itself. So I'll have to use a little space. So atomic mass of this Cl35, that is we are assume it as X. So I'll write in short Cl35, that is X. Okay. Plus atomic mass of Cl37, it would be 100 minus X. What is this 100 minus X? This is the atomic mass of this Cl37. Okay. Just to save the space, I wrote it in short. This is for this thing is for the average this is the atomic mass of Cl35 into X plus 100 minus X. This is for Cl37. Okay. So divided by 100. Now you can solve this like this. That is 35 point. What is this Cl35? What is the atomic this is mass for this? Now we are given one more information here. The average atomic mass is also given, this one, 35.4534. So we just substitute the value here, 35.4534. Okay, equals to, now substitute the value for this also. This is given as 34.968 here, this value. And plus now 100 minus X. This is the atomic mass for the isotope Cl37. Now you can write here 36.956 into 100 minus X. Okay. So this is 35.968 into X. Now divide it by 100. Now you solve this. Now you can solve in very easier way for you. So this would be cross multiply. So I'll write on the left hand side 34.968 into X plus 36.956 into 100 minus X equals to, now this figure multiplied with this 100, cross multiply. So you will get here 3545.3, means this 35.45 multiplied by 100. So I directly written here 3545.3. Okay. Now further you can solve 34.968 X plus, now you solve the bracket here, multiply this with 100. Okay, so you'll get your 3695.6 minus 36.956 into X equals to 354.3. Okay. What did I do? I just solved this bracket here. Now you can write further. This can be written in this way also, minus 34.956 into X minus, here you can write 36.956 X equals to, this can be written as 3545.3 minus 3695.6. So what did I do? I just transferred this from this left hand side to the right hand side here. Okay. So when I do this, this will become minus. Okay. Now, if you solve this thing, you will get minus 1.988 into X, okay, equals to, this will be again minus 150.3. Now you can easily calculate for X. So right here, X will be equal to, from this step, this thing. You can proceed further. X will be equal to, just cancel out those minus sign, and 150.3 divided by 1.988. Okay. So if you solve this, you will get the answer as 75.60%. So x, you got the answer here as x equals to 75.60. So we assume that x as for the CL35. So the answer for the abundance, percentage abundance of this CL35, it was found to be 75.60. Now the total should be always equal to 100. So 100 minus 75.60 equals to 24.40%. So here percentage abundance for here CL35, it was found to be 75.60%, isn't it? And for percentage abundance for CL37, it was found to be 24.40%. So I tried to be everything on the same slide. So in this way, you can calculate the percentage abundance if the atomic masses and the average atomic mass is given and vice versa. Now you can proceed for the next problem on this. Neon is naturally available as Ne20. This is the atomic mass of this neon, and 22. These are the two isotopes of neon. With average atomic mass, it is also given. Now calculate the relative abundance of the heavier isotope. So you can solve the same this problem on the same lines as we did earlier for the earlier problem also. Suppose the natural abundance of neon 20. This is the percentage abundance of this neon 20 dx, okay, as we did in the earlier problem also. And neon 22, if you assume as 100 minus x. Okay. Now you can calculate the average atomic mass, which is also given. This is the same problem. You can solve this on the same lines as we did earlier. So average atomic mass will be equal to atomic mass of neon 20, which we assume as x, plus neon 22, atomic mass of neon 22, that is 100 minus x, okay, divided by 100, because we are calculating your average atomic mass. The value for this average atomic mass, it is given, that is 20.2. So you just substitute here 20.2 equals to now 20 into x, okay, this is for neon 20, plus 22 into 100 minus x divided by 100. Now you solve this, cross multiply this 20, 20, okay, equals to 20x plus 22,000. Just solve this bracket here, 22,000, 2200, sorry, minus x divided by 100. I'm just solving the bracket, nothing else. Now 2020 minus 2200 equals to 20x minus 22x. Okay. So here you'll get, right here, when you solve this, you'll get here minus 180 equals to minus twice x. So x will be equal to 180 divided by 2, which is found to be 90. Now for this neon x, what we are assume, x as for neon 20 for this one. So x is found to be 90%. So the percentage abundance for this neon 20, it is 90%. And for neon 22, it will be 100 minus 90, which is found to be 10%. Isn't it? So this is the way you can solve the problems based on this. Now the next, we'll proceed for the next concept, that is about the molecular mass. Now the ratio of, what is this molecular mass or the molar mass? The ratio of mass of one molecule. This is the ratio of mass of one molecule of a substance to 1/12 of mass of one atom of carbon 12. Okay. So it is the ratio of what? Mass of one molecule of a substance of which you are supposed to know the molecular mass. To what? To 1/12 of mass of one atom of carbon 12. Or it can be defined in this way also. It is a number. Another definition you can write. It is the number that indicate comparative mass of a molecule of a compound. Isn't it? With respect to 1/12 of mass of 1/12 of mass of one atom of carbon 12. Meaning is same, and it is expressed in atomic mass unit. Now this gram molar mass, it is expressed in gram molar mass. Okay. So this is the molecular mass. If you read out this carefully, you will come to know that the meaning of both the sentences is one and the same. So it has to be compared with one atom of carbon 12. Now the gram molar mass, it is the molar mass expressed in grams. Since it is a ratio, there would be no unit for this. But if you express in want to express in gram, so that is called as the gram molar mass. Okay. So gram molar mass is the molar mass expressed in grams, nothing else. Means you just can put the gram sign or gram unit in front of this, that will be your gram molar mass. So molar mass expressed in grams. G. Now molecular mass, it is the sum of atomic masses of the element present in the molecule. So the easiest way of calculating molecular mass of any molecule, suppose methane is the molecule CH4. So how will you calculate the molecular mass of this methane? So that will be the addition of the atomic masses of the element present in a molecule. So here are two elements are there. One is carbon, another is hydrogen. So you can add up the atomic masses of this 12.011. Since there are 4 hydrogen atoms, so it has to be multiplied by 4 into 1.008. So if you add up this, you will get 16.043 joule. That is the unified mass. So this is the molar mass or molecular mass of methane. Now some substances like sodium chloride, they do not contain discrete molecules as their constituent units. Means positive and negative entities, they are arranged in a 3D structure. Means I'm talking about the ionic compound like sodium chloride. This sodium chloride is surrounded by 6 chloride ions and vice versa. So when you talk about the sodium chloride like compounds, which we call as the ionic compounds, so instead of molecular mass or molar mass, the word that is the formula mass is used. Okay. So what is the difference between this? Is nothing but the same. But instead of this, if you use the word formula mass, means it is to be related with the ionic compounds. So the formula mass is calculated instead of molecular mass. So for this formula mass of sodium chloride, you can easily calculate. Just add up the atomic masses of the elements which are present here, sodium and chlorine. So 23.04 plus 35.5. If you add these two, you'll get 58.5 unified mass. So this is the formula mass for sodium chloride. So when we use the word molecular mass, it is for the covalent compounds. Or when we use the formula mass, it is to be related with the ionic compounds. The way of finding out both the things, it will remain the same. So here the one more concept we are left with, that is the mole concept. Now, what is 1 mole? 1 mole, it is the amount of substance. 1 mole, it is the amount of substance. Many problems are asked on this mole concept, remember. So you must be very clear with what is 1 mole. So this is the 1 mole, it is the amount of substance that contains many particles, as as atoms, molecules, particles. When I say particles, it might be atoms, it might be molecules, might be ions, or even electrons also, equal to the number of carbon atom present in 12 gram of, it is 12 gram, this is G, 12 gram of C12 or 0.012 kg. Is in this much grams, what 12 gram of carbon atom, how many or what is the amount of substance that contains particles? It might be atoms, molecules, ions, or electrons, which should be equal to the number of carbon atom present in 12 gram of C12. That is called as the mole concept. Now, in simple way, the mass of C12 atom was determined by mass spectrometer, and it was found to be C12. This thing I explained in earlier videos also. So for this mass of this C12, it was found to be mass of C12. It was found to be 1.992648 into 10 raised to minus 23 gram. Okay, and 1 mole of carbon, it weighs equal to 12 gram, and the number of atoms in it will be equal to 12 gram divided by 1.992648 into 10 raised to minus 23, 12 grams per mole of C12. Okay. So if you divide this, you will get the answer, that is 6.022137 into 10 raised to 23 atoms per mole. So here this 1.992648 into 10 raised to minus 23 grams per C12 atom. Now you will get this thing, which is nothing but, we call it as a Avogadro's number. This is nothing but the Avogadro's number. So this is the way you can get the answer for this Avogadro's number. Now 1 mole. Is 1 mole, that is 1 gram molar mass of a substance. It contains 6.022. You can restrict up till here, 6.022 into 10 raised to 23 molecules. So I'll explain this with the, I have to add one more slide here. Okay, so I'll explain in simple way what does it mean actually. Suppose 1 mole of carbon dioxide, that is 44 grams of carbon dioxide, contains 6.022 into 10 raised to 23 molecules of carbon dioxide. Okay. So when I say 1 mole of CO2 means what? That is the 44 grams. So how do I get this 44? This is nothing but addition of these atomic masses of carbon and oxygen. So this carbon is nothing but 12, and each oxygen has got atomic mass equals to 16. Since there are two oxygen atoms, so 16 into 2 means 32. So 32 plus 12, it is coming out to be 44 grams. So when I say 1 mole of carbon dioxide, means it is equal to 44 grams of carbon dioxide. So it contains Avogadro's number of molecules. Another way you can write 1 mole of sodium, that is 23 grams of sodium. It means, okay. So it contains again Avogadro's number of 6.022 into 10 raised to 23 atoms. Now here I wrote molecules, here I wrote atoms. Why? Because this is a compound. So this compound will contain molecules, and since this is an element, it must contain atoms. Okay. So this is the way you can go for the concept of mole. Now 1 mole of different gases, when you apply this to the volume, this is again a very important part to be discussed. 1 mole of 1 mole of different gases. I'm talking about the gases now, having different molar masses. When I say different gases, means the molar masses will be different, having different molar masses. I hope you are getting me. Masses occupy the same volume, occupy the same volume of 22.414 liters at STP. STP means standard temperature and pressure, and it contains 6.022 into 10 raised to 23 molecules. Means if you are asked to express the molar mass to be converted into volume, so this figure is important. If you are asked to convert this 1 mole of gases into number of molecules, so this Avogadro's number is important. Okay. Now, in short, you can write number of moles, which is denoted by small n. What is this small n? This is number of moles. Number of moles equal to mass of the substance. Mass of substance divided by molar mass of substance. This is the one way we can find out the number of moles, molar mass of substance. Or n will be equal to, n can be calculated, number of molecules if number of molecules are given. Means this equation you can use if the mass is given. If number of molecules are given and you are expected to calculate number of moles, so you can write number of moles divided by Avogadro's. This is very important. These conversions are many a times you will need. Now, if the volume is given, how will you calculate the number of moles? That is n. So n can be calculated. Volume of a gas at STP divided by 22.414 liters. So these equations are of very much importance when you are expected to solve the problems. This conversion of mass of the substance into moles, number of molecules into moles, and volume of the gas into moles. Okay. So this 22.414 liter, this is called as the molar volume. This is called as the molar volume. So in this way, you can be able to solve the problems of this. We'll be discussing about the problems based on this in the next lecture, or rather I will post a video on this also. How will you solve the problems, or how will you make the conversion of moles into molecules, or molecules into moles, or the mass into moles, or moles into mass, and so on. Thank you.